Hello and welcome to this discussion of thermal boundary layers. We're going to go a little bit more in depth than we talked about in our last video. And we're just going to talk about some of the approaches to analyzing boundary layers a little bit more quantitatively. So we have two basic approaches when it comes to deriving equations for the boundary layer. The first is the classical approach, where we derive equations for the momentum and energy, and we solve those equations to come up with the temperature gradient. Now this approach is exact, but its application is a little bit limited. Even for very simple cases, this still requires numerical solution. We can come up with equations, but those equations don't have analytical solutions. And even then, we can only obtain those equations for laminar flows, where we can neglect turbulence. Now, we also have the approximate method, the Kármán momentum integral method, where we use an integral instead of a differential approach. It does require us to use some assumptions and some empirical relations, so it's not as accurate as the classical approach, but it can be applied to a wider range of conditions, especially turbulent flows. Now, we're going to start by looking at the classical approach just to demonstrate the process. So we're going to assume steady state and incompressible flow, and we can then simplify the mass, momentum, and energy equations based on the incompressible flow assumption for conservation of mass. We can also look at this equation for the linear momentum. And then we also have our first law of thermodynamics. Now we're going to make some assumptions, and I'll describe those in just a moment, but we're going to eliminate a lot of these terms. So as we move on, we're going to assume the flow is laminar. That makes it easy so we don't have to worry about turbulence. We're going to assume the properties are constant so they can be removed from the derivatives. We're also going to assume that the thickness of the boundary layer is small, which basically means that the gradients in the x direction can be neglected compared to those in the y direction. We're also going to neglect the body forces and the energy generation to eliminate those terms from the problem. And we're going to assume that there's no pressure gradient in the x direction, that the free stream velocity is constant, and then from the Bernoulli equation we can say that the pressure is also constant. So when we make those assumptions, we can then reduce this to a 2D problem. We're only interested in the x and the y directions along the plate and away from the plate. So we can actually neglect the differential equation for the y direction velocity. That can actually be obtained from the continuity equation. And then we need to specify appropriate boundary conditions for this problem in order to solve it. Now, since we've assumed incompressible flows, you can see that the continuity and momentum equation don't have any dependence on temperature except through the fluid properties, but that's usually small, the kinematic viscosity. So for incompressible flows, it's convenient because you can first solve the velocity and continuity equations for the velocity field and then solve the energy equation for the temperature field. So it allows us to what we call decouple those equations. It's also useful to note here that all three of these equations have essentially the same form, especially if you look at the momentum equation and the energy equation. They're almost exactly identical, and you can see we have a momentum diffusivity and a thermal diffusivity here. So because these equations look the same, we can say that once we've solved the equations, the solution should look the same. The boundary conditions might be a little bit, but in general the solutions should be very similar. So we can make some observations. As I said, the form of those equations are similar, so their solution should look relatively similar. We can also look at the relationship between nu and alpha, the kinematic viscosity and the thermal viscosity. And we can actually say that that is what we call the Prandtl number. That ratio is dimensionless. It's a dimensionless number called the Prandtl number. So nu, the kinematic viscosity, and alpha, the thermal diffusivity, both represent molecular behaviors, molecular diffusion, and so they have the same dimension. If Prandtl number is equal to 1, then these two numbers have the same value, and u and t will have identical solutions. For incompressible flow, as I said earlier, we can solve for u first, no dependence on temperature. So we can use our knowledge of fluid mechanics and deriving the boundary layer equations, and we can see that the boundary layer is going to depend on both the Reynolds number and the Prandtl number.